Hello everyone, I'm Victoria. This is my final project for the course MATH7502. My topic is about PCA principal component analysis. In this video, I will introduce the definition of PCA, how does it work, and its application via Jupyter Notebook by using Julia. Firstly, I will talk about how does PCA work. There is a dataset of vector observations x1 to xn. Each of them has p dimensions. The archetypical algorithm for dimensionality reduction is principal component analysis. The idea is to choose a suitable dimension k, which is less than p, and create a k-dimensional vectors x1 tilde to xn tilde, where for every observation I, xi tilde is equal to v times xi. Here v is a k by p matrix. Each row of v is called a principal component as it takes a linear combination of xi and creates a coordinate in xi tilde. The act of carrying out PCA is the act of determining k, finding v, and analyzing the reduced dataset x1 tilde to xn tilde. Here I will use a famous dataset, iris flower, first used in the 1930s. The iris flower dataset is a 4 by 150 matrix. It has 4 variables, such as sepal length, petal length, and so on, and it has 150 observations. Here I will use the fit function in the package to show the process of PCA. I will explain the meaning of the parameters. For example, the max out time. This is redundant in our case. However, in other cases, it can be used to limit the number of principal components obtained. The Plateau setting indicates to stop when the cumulative variance is greater than 0.999. The default number is 0.99. The resulting model object can be queried. Here, the projection function returns a matrix where each column is a principal component. Here we can see the size of X is 4 by 150. Then I will use some mathematical functions to verify this fit function. Let me set a data matrix A, which is a n by p matrix. I will find the sample mean along each row of A and subtract that mean from all p entries in a row. Now each row of the center matrix A has mean 0. The variances are the diagonal entries of the matrix A times A transpose, and the covariances are the off-diagonal entries of the matrix A times A transpose. So the sample covariance matrix is defined by A times A transpose divided by n minus 1. Here, this code shows the centered mean covariance matrix. This is the sample covariance matrix X. I use another two codes to verify the S. They are the same. Actually, the orthogonal eigenvectors of S are singular vectors of A, which means they are the principal components of A. So I made diagonal sigma, where M is a vector of column eigenvectors V1 to Vp. The corresponding eigenvalues are lambda 1 to lambda p. The head sigma is equal to the sum of m times diagonal lambda 1 to lambda p times m transpose. So the head sigma can be expressed via the sum of rank 1 matrix. In the next, I will use the SVD function to decompose matrix A. SVD means the singular value decomposition. Here we can see the U factor matrix. It is the same with M. What is M? Let's recall M. Here, M is the projection of the model. And in this code, we can see that the principal values of the model is equal to the square of singular values. All of them are zeros. This code returns the normalized variances associated with each principal component. And then I use the first two columns of the matrix M and use its transpose to time X. Each column represents a data point via two principal components. The reason why I choose the first two components of matrix M, the reason is here. I plot the principal component variance and the cumulative variances. As we know, the original data X has 4 variables, 1, 2, 3, 4, and the blue line shows that there is an elbow point here. This is the reason why I choose 2. Then I use the scatter function to show the data points. Here we can see there is a obvious boundary here, and all of the data points are separated into 2 groups. That's all. Thank you for listening.